Hey everybody, hope you're all having a great day. Welcome to yet another episode of YFTT Tech Talks by engineers for engineers. Today we have with us, let me turn off this music. Today we have with us Brian Whitmore, solution architect here at Yugabyte. He's a member of our star-studded SE team. The SE team works closely with customers and helps them make Yugabyte work for best for them. And today, he's going to explain how YugabyteDB provides uninterrupted service during disk outages. Over to you, Brian.
Thanks, Prem. Sometimes I have some trouble with my network if I leave my camera on. So not everyone knows what I look like. I'll go ahead and shut my camera off. But
now they know.
Now they know. So we'll head right into it. So um, the notion of a gray failure is it's one of those things that's a little bit hard to pin down. In that it's a term you might not have heard before. Generally refers to a situation where some of your customers or some of your API calls may be missing performance targets. And in some cases, that can lead to upstream systems having timeouts and failures. And so you want to be able to isolate those and do something about them, but it can be tricky to find them. And so the more tools you have in your toolbox to take some kind of action automatically and not have to wait for a human being to respond to an alert and start troubleshooting, then overall the better your availability is going to be. The fewer missed SLAs you're going to have, so fewer SLA breaches, just better experience overall. And so, especially for external facing applications where somebody might be using their phone, they're not going to have a lot of patience. So you want to make sure things are working very smoothly and consistently. And AWS, they provide some helpful documentation to better describe the different natures of failures that you might experience. And so that'd be some good reading for the interested to kind of dig into that. But in terms of how common is this? How much attention should I pay to this nature of failure? Well, it's part and parcel. You're definitely going to engineer to survive the kind of big failures, right? So an entire cloud region going down, it's going to have a major impact on your business. It's rare, but you plan for it. You either have contingency plans to operate in another region, or more commonly these days, you're running active with part of your application already running in another region. And what's probably more common than that in terms of realistic real life scenarios is some of your customers can't reach an entire cloud region. So there's some kind of routing problem going on somewhere in the internet. It's outside the cloud provider's control. There's somebody behaving badly with routing protocols, and it'll cause some portion of the geography that you serve to not be able to route to one of the cloud provider's regions, but they'll probably be able to route to your other region if you've already put forth a multi-region strategy. So again, this is where active really comes in handy, in that at the application level, you can have your traffic flowing to one region or another depending on what the individual user's experience might be. So those are the big common scenarios that almost everybody tries to engineer into their deployments. But then you get into the things that are smaller in scope, and people say, well, they're not that big of a disaster, so maybe they forget to design for them. But it's probably worth really thinking about them, because these are the ones that happen more frequently. So you might lose service in an availability zone, and it might be because the AZ is having some issue, or it might be because something on your app servers is having an issue. And usually when that happens, it happens to not just one server in an AZ, but multiple servers in an AZ get impacted at the same time. And so you want to look towards strategies where you use more than one availability zone per region, as part of your high availability strategy. And that insulates you from some of these potentially impactful scenarios, such as all the storage getting slow in an AZ or something to that effect. You want to have the uh, the architectural underpinnings already built into your deployment to just leave an AZ if it's behaving badly, because you're already running in another AZ in the same region, so you'll be fine. You won't be in a mad rush to try and reserve machines while everybody else is doing it. You'll already have them. And finally, slow and missed SLAs at the AZ level. And this is, again, just noisy neighbor problems, congestion, things that are becoming more the norm as folks either go full cloud or hybrid cloud. And you just want your infrastructure to be able to, again, step away from servers that are behaving badly. And that's exactly what we're going to address. So as I already alluded to, if you're already active, then you have the best kind of monitoring and alerting that you could possibly have compared to an active passive. You're already doing business in multiple regions, so you're already tracking SLAs, exercising all of that equipment. You know it's hitting your SLAs before you have to fail over to it. And further, if you're paying for it anyway, you may as well run traffic on it. So, really, that should be the norm. And with a technology like Yugabyte, where your data is always consistent, regardless of which region you're operating in, it's readily attainable. So there's no reason not to do it. And then the other component is that you want fast timeouts and retry logic at every stage of the layer cake. So in the database configuration, in your app server configuration, in your CDN code, in your remote applications, everything should be aware of what the SLA is supposed to look like. And if a response is slow, it should be prepared to try that other region or try that alternate channel that you've already provided. And Frank does a really good tech talk from an earlier Friday Tech Talk session about retry logic in general. And in there, he makes a case for it. And I'm just going to double down on that and say that you absolutely should be taking advantage of all this parallel infrastructure you're building, and make sure that at every stage your application pipelines are able to use it. And then, of course, every configuration at every level that allows you to automatically detect and mitigate any kind of failures or bad behavior, you want to use it. Yugabyte provides it. Application servers provide it. The cloud providers provide it in terms of auto scaling groups and things like that. You want to try to take advantage of that wherever you can. It does add some complexity and it adds to your testing, but it's well worth it. And then speaking of testing, test the heck out of everything. If there's a conceivable failure mode, even if it could only happen once in 100 years, Murphy's Law says that it'll happen. So make that part of your chaos testing suite. Exercise it. Make sure everything works when you make changes before you promote the changes to production, and you'll always catch all your surprises before you get to production. So to that end, Amazon provides a service called Fault Injection Service that lets you automate your failure testing. I imagine the other cloud providers have similar services that they also brand. I'm just not familiar with all the brand names, but take advantage of that automation, because you want to make repeating the testing part of your standard workflow of elevating things to production. I also want to mention, in terms of the level of availability that you can configure, I want to make a really strong case for RF5. And I'm planning on writing a blog about why I love RF5. So hopefully that'll be out soon. A replication factor of 3 is basically minimum viable to get fault tolerance in a multi-region scenario. And the reason I say that is because if you don't have a complete copy of data in a region, then you're going to fail over to the second closest region, and your writes are going to have to include that and the third closest region. So the latency that you're able to maintain with an RF3, it just doesn't compare to what you can do with an RF5. With an RF5, you can have nodes down in a region, and you still, between the adjacent AZ and the nearest neighbor region, you still have 3 out of 5 participants in every raft group. So your latency doesn't change when nodes go down, and that's key. So when you're trying to hit consistent SLAs, that's really going to help you. And also, the cost to do it is negligible. So,
Yeah.
Prem, you look like
One
you wanted to
point.
break in.
Yeah. So one point. So RFI is very useful even the case where not just a region failure, but even if you're doing node upgrades or rolling restarts for software upgrades, because you have a copy of the data, another copy of the data on the same AZ or region, immediately that particular replica will be promoted to master without any service interruption.
Yes, absolutely. And so, when you're in a constantly online configuration, especially for user-facing, client-facing apps that, again, if somebody's on mobile, they might be checking at 2 in the morning. There isn't really a nightly downtime anymore. You're always online. So you want that flexibility to be able to do your upgrades even during the day if you're inclined. And, especially with security patches, you want to apply them right away. Why wait till a nighttime window?
Sure.
So going along with that strategy of having, a very robust infrastructure based on having extra copies of the data with RF5, it's very low overhead. It's definitely worth doing. And with that, have all of your network settings primed to fail fast. And, we talked a little bit about, where you do that at even up to the CDN level to make sure that regardless of what goes bump and where it happens, you'll always be able to get around those failures and get to your database and make sure that your business is running. And last but not least, I want to introduce an optional storage management service that you can add to YugabyteDB. It's part of the Yugabyte GitHub. This link will direct you to it, and there's a document in there that explains how to use it. And this is like a systemd service, so it's just another service that you add to your database nodes along with the systemd service that makes sure that the master and T server are running. And this one is focused on making sure that your disks are monitored such that if you're ever unable to write to any of your disks for a period of time, then that node becomes aware of it and can take itself out of the cluster so that it's not holding up anything or slowing anything down. So, in terms of a disk gray failure, this is directly following what's going on with the disks and able to take action right away.
Good point.
So in order to make our cluster very responsive to anything that might happen in the network or related to the disks, there's some tuning that you can do. And most of these G flags have very conservative defaults because a lot of deployments are RF3, and having servers take themselves out of the cluster because the network got slow or the disk got slow would be a bad idea. It would adversely affect performance, and you wouldn't want to do that. So very conservative settings mean that instead, those nodes are going to try and stay in and just ride out whatever badness is happening in the infrastructure. But if you're taking the view that you very deliberately deployed extra copies with RF5 Your target is maintain your SLAs and deliver good quality service at all costs, and you know your infrastructure very well, then you can start to get more and more aggressive on your tuning and take action faster. And so this is a couple sets of settings, a tuned variant that's probably good in most geographies, and then what I'm calling an aggressive variant, which is I've handpicked some locations. US East 1, US East 2, they're about 11 milliseconds apart. And US West 2, it's about 60 milliseconds out. Very stable, very well known, all in AWS. So with that, I know I can get pretty aggressive with these settings, and I'm able to have very fast failover and consistent, reliable convergence after failovers, so that I can provide the best possible user experience.
Hey, let me interrupt you here, Brian. We have about 14 minutes left, 15 minutes left. So I just want to make sure that
right.
it's
Make
a
sure
time
we
frame.
allow time for Q&A.
Yeah, demo too. So.
We're right close to the demo.
All right. Thanks.
Yep. So in terms of what you can expect to see, you're going to see the database failover in 2 to 5 seconds, or detect the failure in 2 to 5 seconds, mitigate it within 2 to 10. So that'll be 4 to 15 seconds overall. And there'll be a few long tail blips due to tablet load balancing and some other things that are internal to the database. So they'll show up in the charts because the charts are really detailed, but you're basically in business after 15 seconds at the most, and possibly as quick as 4 seconds. Now on the client side, client has about 4 seconds to do its retry, and anywhere from 35 to 120 seconds for the Hikari pool to shake out where it wants to put the connections. You absolutely can do better, and we'll talk about that in the Q&A in terms of things you can do on the client side to get to take advantage of the fact that your database can be available in less than 10 seconds. So without further ado, let me get into the demo.
Awesome.
Just drag this out of the way. And so what you're looking at here is a client application that's generating workload, and it's running on an instance in US East 2, is able to see the entire Yugabyte cluster, and it's
so this is an
got a
RFI cluster, right? So those the orange ones are nodes. The orange ones are nodes, and the blue ones are regions.
Orange ones are blue ones are regions. The orange ones are AZs, and then if
AZs.
you zoom in on the individual little, looks like an LCD projector, but it's actually supposed to be like a server. But there you see the IP addresses of the individual nodes. And so here we can see the aggregate throughput from this client is about 5,000 operations a second. That's a split between 600 or 700 writes a second, and the balance are reads. And you can see the average latency tracking to around 16 milliseconds, 46 milliseconds for the writes, and then the reads are much faster. And then I've got another
1 minute.
instance.
So is this East 1, East 2, and West? Is it?
So that application is running in East 2.
Okay.
And then I have another instance of the same application running in East 1. You can see the latency is just much better, right? But it's writing to the same database, and so I've actually got both of these running. Now I've only got enough screen to really show you one, so I'm just gonna leave the one up here as a full screen background while we go take a look at the cluster itself. And as we mentioned, it's an RF5 cluster. So it's running on 10 nodes, and they're located in East 1, East 2, and West. But I've got 2 AZs in East 2, 2 AZs in East 1. So 80% of my servers are serving traffic. And that's another reason I like RF5 is I can use 80% of my servers instead of just 2/3. And so if I take a look at my nodes, you can see that currently this one is the master leader. And if I click on that, that'll take me into the EC2 console. And we're going to do the fault injection using AWS to do that. So I'll be doing a disk fault injection. So let me just come down here and say I want storage. And scroll with me. Come on. It's never fast when you're doing a demo, right? All right, so this volume right here, this 10 gigabyte volume, that's my data partition. And under actions, I've got fault injection. And so I can either write a fault injection script, or if I want to go the no code route, I just pause IO. And you can still see my.
So effectively, you're disabling the disk, right? So Brian, effectively, you're disabling the disk.
But the interesting thing about this kind of a failure is it does not return any errors to the operating system. The disk just goes silent. And so it would be real easy for an application to take action if it started getting errors. But in this case, it just goes silent. And so it's up to that storage monitoring service to detect this and take action quickly.
So typically, the storage monitoring service or operating system, how long does it take for it to identify that the disk has been disabled?
Anywhere from 2 to 4 seconds. All right, so seconds. I told it to make a failure happen, and then it's going to schedule the task. And let me get that window back and just move it out of the way here. And then once it, yep, there it goes.
There it goes.
Yeah, it takes AWS a couple seconds to do it, and then that was it. That's the failover. So if I zoom in on this, let's see if I can, yeah, we'll zoom right in on this. That's about, looks like 6 seconds it took for us to get our throughput back.
Okay. So there was a small interruption of service, but we did not lose any data, right? Because of RF5?
Correct. Yeah, we did not lose any data. All that happened is it took a couple seconds for the client application to route around the failure, and there was a couple seconds meanwhile while the database itself paused writes for correctness until all of the raft groups had elected appropriate leaders, and then you're back in business. So it's a very quick operation. So I know it was 20 minutes of talking just to get to that 6 seconds, but
oh yeah, that was a pretty cool demo. It's very, very clear. In fact, the term disk grayout, it's a very recent term that has been come into use. In fact, it typically comes from where computer systems GUI user interfaces show disabled devices in the gray color. So that is how the system knows that the disk exists, but it's inaccessible. That's how the disk grayout term comes out.
Yep, and it's really it's a situation that might if you were waiting for a human to notice an alert and then start exploring where the problem came from, that might take 5 minutes, 15, 20 minutes. This, is just a brief blip, and nobody ever realized there was a problem. You just stay in business.
Do we send out an alert? Actually, it would have been, we should have checked this earlier. So do we, on an YBA system, do we send out an alert for this? I'm guessing.
Not directly at this time. So what you're going to see in terms of alerts is you'll get the alerts for T server down, and if the node happened to be a master, you'll also get the alert for master down.
Okay.
The current version of the storage monitor does not directly have alerting and monitoring beyond what it writes to log files.
All right.
And if you can't write to log files because your disk is frozen, that's sort of moot anyway. There is some planned work. I don't know exactly what release it's targeted for, but we do have some work coming up to make it more of a first-class service where it will be directly monitored and you'll be able to alert on it.
Okay. So as of now, the system administrators will know that a T server switch was made, a redirection happened, but they would
Right.
not know that the disk failed. You would not
Right.
even, the applications would not even notice it. Okay.
Right. So the alerts that you would receive would be basically at the T server and master level, telling you that it went out of service. It wouldn't tell you why. Now, the interesting thing about this kind of failure is when they happen in real life, it's usually because some piece of infrastructure in an availability zone got hung up. And it doesn't just affect one node when it happens. So your dashboard would probably say, just depending on how many nodes you have in each availability zone, that you lost some of them. And also probably other applications that you're running in the same AZ are going to be in some way impacted by this kind of thing. So, where I've seen like sometimes depending on your cloud, 3, 4 in the afternoon, the disks might always get slow. Not naming any names, but if you run there,
I know.
So that's what the demo looks like. And I also when we put the slides up, right? We share the slides.
Yeah.
I've got not only the G flags in there, but also the configuration for the workload simulator as well. And normally in your environments, you'd want a longer max lifetime on Hikari. But you know what? Let's go ahead and open it up to Q&A because
I don't see any questions. I don't see any questions from users. Alan has been pinging the audience about questions. No one has responded.
All right. I guess they're just super impressed and.
Yeah. No, but that was a very cool demo. I mean, I was very not very comfortable doing this live, but you pulled it off very nicely.
A lot of people say never do a failover demo live, and
exactly.
I gotta say, if you don't believe your product can do it, sure, but if you've been through it 100 times and your product is robust, absolutely do it live. If you don't, are you really building a robust product?
Yeah, but I'm glad that it worked. It worked as expected. So.
Yeah, well, I mean, I'm relieved too.
All right.
Yeah. So on the client side, the really fancy technique that some of our customers do is they actually run 2 Hikari pools at the app server level, one pointed at the region they're running in, and one pointed at the neighboring region, and then they do the retry logic based on a client-side timeout in the app server. So they'll issue a SQL statement, and if that doesn't complete within the allotted time, then they'll retry on the other pool.
So we have a question from Srinivas Kurup at Fidelity.
Mm-hmm.
So is this deck available to share? Primarily, he's looking for the G flag settings.
Yep, absolutely. So we will be sharing this afterwards, and also I can just email them to you.
And no. Also, let's make sure that these settings are updated in the docs.
That's a good idea.
Yeah, let's do that.
All of the G flags I used are described in the docs.
Yeah, but I do not
all it says there is their default.
Right defaults. Yeah.
Yeah.
And from Huan. So how do load balancers affect failovers?
So the load balancer is usually checking to see if the Postgres port is open. And there are some situations where the Postgres process might be running on a node, but it can't talk to some or all of the tablet servers. So that can happen if you're having network problems. And this is why it's a really good idea for the client if it issues a SQL and doesn't get a response in the allotted time. It's a really good idea for the client to be looking for that and to try again on a different connection, because chances are with a load balancer in play, if you try on a different connection, you'll land on a different server.
Yeah.
And so you've got a really good chance in that regard of having your query go through. And the client retry logic can be very quick. If you know that your application is consistently under 200 milliseconds, you can say, if I don't get a response in 500 milliseconds, try another connection, right? So this is fast enough that a user wouldn't even notice that the client had to do a retry.
Yeah, so even if the client connects to a different node, if it's requesting for data on the machine where the node is failing, the disk is failing, it still has to wait, and it is absolutely up to the application to realize that not application. So our Yugabyte node to realize that the node has failed, and then it has to do a leader election for that the data on that node to be served properly with a new leader election.
Exactly. And that's why we want to make sure that if a disk is failing, we have that
We have to handle
failing node give up as quick as possible, so one of the 4 other nodes can take over.
Yeah. Good point. So already we are 2 minutes over time. Thank you, and we don't have any more questions. Amazing presentation, Brian. Thank you all.
Thank you very much.